Thank you and good morning. Patrick Gibbs asked me to come and reprise a talk that I gave a couple of years ago that somehow ended up on YouTube, and I wasn't aware of it, but so I had to go back and find out what I had said a couple of years ago. And I've tried to update it a little bit since then. So in spite of the long title, what I really want to talk about is the bottom line is how can we work better together for the state of Washington, academia, industry. My experience, of course, is with Boeing, but I've visited and participated and worked with many other industries related to aerospace, and of course the government aspect as well. And in traveling around the world, I had the opportunity in Boeing to travel for several years to various countries looking at composite capability. I noticed in several countries there was a very good working relationship between the government, the leading universities, and the industry, and they were working together for survival and success. You know, they could not afford not to work together. Countries like South Korea and Taiwan and Singapore, they're very, very good at forming these teams where everybody, all the players are participating and supporting, and they have common goals. And I think that's what we need, and that's what we want in Washington State. I'll skip those. The one line I put down at the bottom, just put that down last night, actually. One of the things that I encountered hundreds of times was professors or CEOs or entrepreneurs would come to Boeing, say, I got this great idea. I think it would help your wings. Who do I talk to? I've been trying to get in the door and I'm frustrated. And there's some answers to that and some homework that has to be done. I'll touch on a little bit of that in this pitch. I want to talk about the opportunity. I'm going to pick one particular opportunity, that is multifunctional nanocomposite materials, and talk about the challenges and the constraints that face that introduction. A little bit about the importance of training, education, becoming familiar, all the parties becoming familiar with each other, and then how could we work together. So over my career, I started at Boeing at, I think, the very earliest stage of introduction of composite materials. And those of us who were working in composites kind of fell in love with it. We all had Steve Tsai's red book on our desk. The idea of going from an isotropic metal to an anisotropic material with layers and orientations and fiber directions and toughness can be added. It was an intellectually fascinating subject to go from aluminum to carbon fiber composite. More recently, we, Boeing and others, have gotten a very strong interest in nano-modified composites, because now we can take the flexibility and the profoundness of composites and multiply that by the proper addition of nanoparticles. And the hope is, and the promise is, that this will lead to a multifunctional material. It's not only going to be strong and carry loads, but it'll also carry electrons and phonons. It'll be electrically and thermally conductive, and maybe acoustically damping. All those things are possible. There are little reports and papers and research projects that suggest that's possible. Now, one of the things that faces any industry, our products are very large. We make space stations and 747s, and nanoparticles are the smallest thing. They're 1/100th the size of a virus. But they're so powerful because they are so small. The surface to volume ratio is very, very large, which gives really a power to the performances. It offers that promise of multifunctionality and the promise of being able to truly engineer a material rather than just accept it off the shelf. So in the past, I can't use my laser pointer, but you look at the vertical axis there, we've gone from fiberglass composites to carbon fiber woven products, and now on the 787 and the 777, we use high performance carbon fiber tape, automated layup. It's tremendous improvements over the past decade or so. And then when we want to protect against lightning strike, we add some more material. That's ancillary material. It's electrically conductive material. And then if we want it to be thermally conductive, we add some more material. And that just provides thermal conductivity. And if we want it to be quieter, we put little pads of acoustic material in there to make it quieter. The promise of multifunctionality is to have one material that can do all of that. Thousands of pounds could be saved on a single airplane if you could remove the ancillary materials for electrical thermal conductivity and acoustic damping, just to mention three. And by the way, all major composite material suppliers have active programs to develop this kind of material, and working with Boeing and others, of course. One of the realities when we first got into nanotechnology at Boeing was around 2005 or 2006. Some people went out and bought nanotubes, stirred them into the resin, made pre-preg, made coupons, did tests, and the results were worse than without the nano. And then we learned the hard way about the need for understanding the dispersion and functionalization of the nanoparticles in the material. And that was a hard lesson to learn. And so the grand dream of making a stronger wing, we had to reduce our ambitions a little bit, and we looked at what can be done in the near term, because the basic strategy was to get some nano into production in some way or another. And two-dimensional applications like films and coatings, I'll talk a little bit more about the benefits of that, or modules and packages, things that can be replaced. That's the near term. So we became more pragmatic with time and education and knowledge and experience. So the interest of 2D is one less dimension, of course, but there are other things. The business relationships are simpler. You don't have to have long-term projects with the company that makes the material that makes the structure of the wing. You can just worry about a supplier that would provide some surface coating or surface layer. It's also less disruptive because anytime you change a material in an existing airplane, you have to recertify the whole thing through the FAA. That's a very, very daunting, and in some cases just stops programs. It's too expensive. But if you can apply nanotechnology in some way that will not affect the substrate or the certification, that's a quick and easy approach. And of course, the analyses are much easier. And the same goes for devices and systems. Systems will probably be more likely to have nano on the airplane than structures. Back in 2005, when we first heard of the word nano, some of us put together, I guess it's a workshop. It was a 3-day workshop. We invited a total of about 120 people. 2/3 of them were from outside Boeing, from suppliers and universities, government agencies, and went through those 3 days and distilled down from hundreds and hundreds of ideas these top 10 or so items. The interesting thing is that this was 2005. If you were to make a list today, most of those would still be on the list because we haven't had that much success. we still want those things. They're not achievable in the sense that they're not in production. You know, you don't see them rolling off some factory floor. So the summary of the applications is there's great promise, but we need to focus initially on the early steps, early achievable steps. And we must have, and this is very important with anything, not just nano, but if you're going to develop a new technology for industry, or like a Boeing, you must have the team together at the start. You don't go do something and then call in the material supplier and say, I want you to make this stuff. You know, they have to be there from day one. And the certifying agency also, we brief the FAA and other agencies on what the visions are first, so that they're part of the team. They come along with us on the path. And so everybody really needs to understand the engineering and the enormous production requirements, very significant production requirements. You can't have a material that has to be made in, wearing white suits and $1 million pieces of equipment. It has to be producible. It has to be on the factory floor. It has to have as little impact, and hopefully no impact, to existing production. If you change a conventional composite to a nanocomposite, it should be invisible to the people on the factory floor. And then the 2D and modular. So one of the things back a few years ago, 4 or 5 years ago, was CANIUS, was an organization up in Canada, hosted or put together a conference in Toulouse. And the whole subject of that conference was the Valley of Death. That gap between academia and research and national labs and production, like Boeing and other large companies. And that's the most difficult part of it. You can make it work, but how do you make it optimal? How do you make it reproducible? How do you make it reliable? And how do you make it low cost, the most important one? And then Boeing will figure out how to make it producible. We do the production part of it. But that was the theme. And this is a cartoon my boss liked to use. Sometimes in industry, the teams and the people are so hard-pressed under such constraints and pressure from schedules and marketing commitments and cost. They see a path and they're going there. And I've had this happen to me. I go to a team that was working lightning strike protection and suggested that maybe we could try looking at some nanocomposites, and got thrown out the door. You know, they don't have time to listen to something, even if it's potentially better. I like this cartoon. This is on the other hand. Here, Dilbert spent 6 months figuring out how to make parsley from pocket lint. Brilliant, but totally useless material. We don't want that. And not just outside Boeing, but there are people inside Boeing that resemble that. So a few years back when a BRT was formed, maybe 4 or 5 years ago when BRT was formed within Boeing, the leadership adopted, strongly suggested, the Heilmaler Catechism. Heilmaler was the director of DARPA, and he's a member of the Academy of Engineering and many, many other successful achievements. And when he was in DARPA and people would come to him for money for research projects, this was not a criteria, it was not a test, but he would suggest, and we did this in Boeing, it was a suggestion. Before you come to the leadership for funding, internally funding, think about these things and be ready to answer these things. What are you trying to do? How is it done today? What's new, and why do you think it'll be successful? And who cares if you're successful, if you produce parsley from pocket lint? Who cares? What are the risks and the payoffs? You have to get a good understanding of that. And how much it will cost, and is it going to take 20 years? Forget it. And then what are the checks along the way that we can test you to see whether you're doing what you promised to do. And so this was sent out to all the people in BR&T, and again, it was not a gate that you had to bring your answers to. It was a suggestion. Think about these before you come talk to us, the leadership, and so you'll be better prepared. So the priorities now, we're still striving for that multifunctional material that can save time and money and weight. That material, if we ever achieve it, will be totally useless unless we have quality assurance. Now, when we went from, on the 777, went from the 67 to the 777, we went from a brittle conventional composite to a toughened composite that was developed by Torre. We didn't have the QA methods to test that material as it came into factory. 40-pound roll of that stuff come in the door. We didn't have the test that would say that every square inch of that material is good. We do now, of course, because it's being used all over the 787. We need the same kind of assurance tests for nanomaterials. If you were going to put some of the work that's been done suggests great performance with less than 1% by weight of nanoadditives. Less than 1% of things that are nanoscale. How do you know that they are where they should be, that they've been functionalized, that they've been dispersed correctly, that they're not clumping together to form a crack starter in the structure? We don't have those now. We have suggestions, and there are people working on it here at WSU, Kitty Zong in the back, but they're not on the factory floor, and they need to be before we get to that point. And who's going to make the material? We need to have, somebody, I think it was somebody from Florida State University brought us a piece of material that was very nice, very conductive, carbon bucket paper. It's like, okay, who's going to make 10,000 pounds of this per month or per year, whatever? That's the question that needs to be answered before we go too far. And it can't be a little swatch. Our processes are continuous. They're rolls. They go on automatically by computer, not by hand. So to the credit of FSU, Ben Wong, who was the director there, he came back about 6 months later and he said, I've got it. It's on a spool. I can make a continuous spool of this stuff. And you're great. You're listening. You understood our needs, our requirements. And of course, it has to be affordable. You can't have a nano composite that costs even twice as much as a conventional composite because you get pushback. One of the realities is that a structural material, even a conventional structural material, has to be more than just strong and stiff. It has to be durable. It has to withstand corrosion and environmental attacks. It has to have a damage tolerance because they're going to get damaged. It has to be producible, of course, and it has to be repairable. And generally, when a project starts almost in parallel, there's an effort to start developing repair methods for the material, because you don't want to get to the point where, I got a great material, somebody's going to make it, but if it gets hurt, I don't know what we're going to do about it. So repair must be done almost in parallel, at least not too much later than the start of the program, so that when it's ready, we're going to know how to fix it. And that was the case with the 787. All composite fuselage and wing, when that got to production, the repair methods were already developed and documented and ready to go. And then the material, no matter how good it is, when it gets to production, when it gets to design usage, there's going to be we won't be able to take full advantage of the material because there's all these other things that we have to consider, all these possibilities that will knock down the usable allowable stress level. Basically, it's the margin of safety that we're going to put in there for damage. And a material might be great. It has some damage, and the repair calls for drilling holes and putting the patches. Well, the holes are going to weaken the structure, of course. So the structure has to be designed for repairability. And then that new material is going to have to go through this whole pyramid. Material property evaluations coming out the ear. They're tremendous. I mean, one test was soaking in hot hydraulic fluid for 3 years. We've got to know the answer to that. And the hundreds and hundreds of other tests. Then subcomponents, and then the full-scale test. And, you know, as you've probably seen, ultimately Boeing will break a wing just to make sure it's not too strong and not too weak, not too heavy enough. But the upper portion of this is certified mostly by analysis. When you go to the FAA, you don't just have a bunch of test data. You have analyses that have been proven. The larger tests are not to interrogate the material or the structure, it's to verify the analyses that were used for the certification. What we really need is analysis at the lower end of this, especially when we come to multifunctional materials. We cannot afford to test them the way we do conventional materials because it's exponentially greater number of tests in years to accomplishment. So we really need a modeling capability that can give us answers and the same kind of analysis for the raw materials as we have for the structures. So the material itself will go through not just development, but suppliers have to be ready. We have to, it's partially technical, partially business. You've got to work with your suppliers so that when you're ready, they're ready. You have to develop not just a material, but a manufacturing process. And the process gets qualified and certified just like the material. How you make that, there'll be a big fat process document, process control document, how you make parts with that material. That has to be developed in addition to the spec for the material. And then going up the pyramid. So the reality is, and many people that come knock on the door and say, I've got a great idea, the time frames for this, all of what I've just talked about, can be very long, 10 years or so. The material that went on this 777 empennage, I was working on it 10 years before the airplane flew. Critical is the supply chain, because there's more than one supplier. There's a supplier of the fibers, the resin, the nano, the raw material, the pre-preg. The subcontractors are going to make the parts out of that material to your or our specifications. The material must be demonstrated to be consistent. First of all, we must know what the material is from the atom on up. And then they need to be able to reproduce this roll after roll or batch after batch, whatever it is. And then, of course, we need the quality assurance methods. And I reiterate, the most important thing for going to a multifunctional material is modeling. We don't have that. We have modeling at the atomic level. We have modeling at the structural level. We don't have them connected. We don't have models for the connecting parts. Again, I think I just said that. So this is another one of my boss's favorite slides. Somebody said, I just developed a new material. Would you test it and see if it works? And Boeing is not a test laboratory. It's not your test laboratory. First of all, the first step is not to bring us some patch of material, which has actually happened often. They will come into a conference room and lay down a piece of material on a table and say, here's what I just invented. Here's what I just developed. I think it'll be great for you. how much do you need to test it and find out? But they don't know the fundamentals. A successful entree, a successful visit will be by someone who understands the technical requirements, someone who knows the quality requirements, someone who knows the production, and that I can't just make a little patch of it. It's got to lead to a mass production. And there are certain formal paths through that, business people who understand all those things and then can direct you to the right technical people. So I think I said that already. So the bottom line, it's got to introduce a new material. For instance, the 787 right now has a very successful material. You want to replace that with something better on the next airplane. It has to be, number one, extremely affordable, and that includes not just buying the airplane, but how to cost to operate the airplane, to maintain and repair the airplane, and what's an airplane worth when an airline decides to get rid of it and buy a new one, because they work their way down through the levels of airlines around the world. And then it needs to have not just incremental performance benefits, but really significant, standout, irresistible performance benefits and payload range and speed. And cabin features. On the 787, the composite fuselage enabled the windows to be 20% larger because fatigue was not an issue. And that's a great, people like that. And environmentally friendly is absolutely a requirement. So, I want to get through this part pretty quickly, but one thing I would suggest is I thought that this experience was very, very successful. It's dated, but that model I think would work in the future. We had, 6 nano workshops over a period from 2005 to 2008. They were all multi-day. They were in rooms like this. We had 100, 150 people come, hands-on talking, interaction. The strongest feedback I got from the external people was, thank you for letting me know or let me understand a little bit more about what Boeing wants. In these 3 days, I've gotten more in these 3 days than I got in the past 3 years, trying to figure out what your company wants from us. And as it was very, very hands-on, rather than have a roadmap software on a laptop projected on the screen, we chose to use rolls of paper and string, and everybody got down on their knees and started building these roadmaps. In this picture, there are professors, CEOs, FAA officials, engineers from Boeing. They're all down there pasting, cutting, and when that was finished, they owned it. They owned that roadmap. In fact, we could hardly keep them. They want to know, when do we come back and update it, Education, starting out at the lowest levels. One thing I want to mention down at the bottom here is WSU has the Imagine Tomorrow High School Science Fair every year. The next one is in June, I think. And I've been a judge for the last several years, and I see a very big increase in the number of high school projects that are using or based on nanotechnology. Sometimes they're amazing, and you wonder how could they do so much in so little time with no money. And then sometimes they're kind of naive, and so the education part of it is very important, but it's coming whether you want it or not. It's coming from the lower levels. A couple of weeks ago I was at Penn State. Penn State has a very large NSF grant to provide nanotechnology education to community college level people. And they call it Nanotechnology Applications and Career Knowledge. I was one of 15 industry advisors. They have the IAB, and once a year we meet and review their progress. But it's very interesting because they're focused on the community colleges. And those are the people that can help Boeing more immediately. And I didn't put any details up there, but you can search that on the web, and there's tons of information on it. A few years back, there was a University of Southern California and NSF held a nano education workshop, and this is a summary of many of the sources that were identified. And then also the organization ASME, American Society for Mechanical Engineers, very eager to help. They have, in this case, they have something called boot camp, where they come to, actually they came to University of Washington, and mostly Boeing people were there, I think. But they can teach you, and they're available, and it's very good. So as far as working together, I think why we collaborate, it's the third one down. I like harvest world-class ideas and technologies. Many of our travels, we found universities or small companies that were already had solved problems that we were just beginning to think about. So we're not going to go figure out how to do it ourselves. It's already done. We just now have to figure out how to work with these people. And that reduces development time and overall costs. So those are two benefits for collaboration that I like. Boeing has many levels of collaboration, from funding a professor here at UW to establishing a branded research center. In Madrid, there's a research center, a Boeing research center. Sometimes you take a Boeing engineer or a Boeing scientist and put them at the university for a year and let them sit there and act as a flow between that university and Boeing. There are consortium memberships, so we belong to, I know, a number of those. Composite Center at University of Delaware, for instance. But the best thing is that getting people out into the world from Boeing, get rid of that provincial attitude that you have, technological provincial attitude, and then having them come back at some time. I was offered a chance to go to spend a year in KAIST University in Korea, but my boss said they had better uses for me for 1 year. So I had to pass that one up. So the teaming formula for success: government, industry, academia, together as a team, working together, suppliers. And we have various, this is kind of a Boeing specific thing, but there are different relationships with the universities, from funding a specific project to identifying a strategic relationship. And what we need in the future, of course we need new technology. The next airplane must have new technology, just like a 787 leapfrogged from its previous aluminum airplane. Teaming is absolutely essential. You might as well give up if you don't have that in place. And training, because we tend to make too often the same mistake over and over again. Sometimes I hear people would call me up and tell me something, and I said, that's not going to work, and we decided that 6 months ago, but you didn't hear about it. So training can remove that uncertainty and that lack of communication. Consistency, even though we're an airplane maker, or Boeing's an airplane maker, we had people that understood the chemistry of the materials that were being supplied, down to a level that required a PhD in chemistry. Quality assurance methods are repeated over and over again, and modeling for multifunctional materials. And that's a summary. I think, looking back at that picture, what is developing now is in the past we had academics doing research in the lab, and we had engineers doing production engineering and design. There lacked a class of individuals, or they lacked a profession that specifically was trained and educated to bridge that gap. Some people call it technology brokering. But I think that's developing now, and that's good, and that's going to help us. And the last word, and it's always the last word, why do it? Airplane capability must be improved, payload, range, speed, etc. And TAROC, which is total airplane related cost, procurement, operations, repair, maintenance, and residual value. Those are if we don't have those, then everything else is just a waste of time talking about it. So thank you.